Alright guys, so today we're kicking off with looking at a little bit of Newton's second law and how we're going to solve some problems with it. Most kids are going to look at this and they're going to say, Mr. Lennox, I'm going to solve it this super easy way, and that's how I'm always going to solve it. And I'd say that would be awesome, but if we have an initial velocity, like I'll show you in a later problem, you got to do it a little bit different. You got to do it this way, and so I'm showing you both ways so you can kind of get a feel for that. Okay, the problem looks like this. A 42 Newton force directed 15 degrees west of north acts on a 56 kilogram rock sitting on a frozen pond. So we're going to assume no friction there, so the rock can slide with no friction. And the force is going to act for 3 seconds. How fast will the rock be traveling at the end of the 3 seconds? Okay. Well, guys, we know that if you have a force on a mass, Newton's second law says it's going to accelerate. Okay. And then we're looking at it's going to accelerate for how long? 3 seconds. We know its initial velocity was 0. We can use kinematic equations to solve that thing. Okay? So if we look here really quickly, here's our rock sitting on the pond. There's our force of 42 newtons acting 15 degrees. Okay? Now the easy solution to this one, and this one you can solve this way, and it's totally fine, is we use Newton's second law, F equals ma. We know the mass of the rock. We know the force on the rock. And we simply calculate its acceleration, 0.75 meters per second squared. Pretty straightforward. Okay. Now, guys, which way is the rock going to accelerate? Well, the rock's going to accelerate in the direction that you're what? You're pushing the rock. Okay. So quite simply, if we wanted to do its acceleration, we could say that acceleration is happening in a direction 15 degrees west of north, right? Acceleration is a vector quantity, so including the direction is pretty important. Okay? Now, guys, knowing that our initial velocity is 0, that goes away, and we can calculate our velocity by taking v equals v naught plus at. We know the acceleration, we know the time. If you multiply those two together, you get a velocity of 2.25 meters per second, and the velocity it's going to be going, the direction it's going to be going is going to be in the same way that you were pushing it, which is going to be 15 degrees west of north. That, I think, is a really simple problem. You just have the mass and acceleration, you find it, you plug it into some kinematic equations, you get the answer. Okay? If the rock is stationary to start with, that is how you can always solve them, and it's super easy. Okay? What's going to happen is if the rock is moving to start with, then you're going to have to break it into its x and y components because it's going to be moving in a certain x direction or y direction. And so let's look at this second solution. And I know it's harder and I know it's painful, but when we get to a problem where the thing is moving initially, then we're going to have to solve them this way. Okay? So let's look at this one. What we did, guys, is we broke its acceleration down into an x component and a y component. If you come back here, guys, can we break the force into an x component and a y component? And we've done that so many times with the cosine sine. You guys should be proficient there. Okay? So we come up with that for our fy and that for our fx. If we come over here, we know that Newton's second law, F equals ma. Well, that's all I've done is put it into the x direction. The force in the x equals the mass times the acceleration in the x. So when we put in our force in the x direction and our mass, we come up with an acceleration in the x of that. When we put in our force in the y and our mass, we come up with an acceleration in the y of that. Does that kind of make sense to you? Okay. Now, guys, it's really simple. If I use kinematic equations, I can come up with a final velocity in the x direction. So we use our a in the x, which we just solved for, and our time, and that's going to be our velocity at the end of 3 seconds. That's going to be our velocity in the x direction. Okay? If we come over here, same exact formulas. We're going to find the velocity in the y direction at the end of the 3 seconds. Okay. Now, hopefully, if we put those together in the Pythagorean theorem, we should come up with the same magnitude of 2.25. So let's check that out really quickly. If we take Vx squared plus Vy squared and take the square root, we come up with a magnitude of 2.25 meters per second, okay? Which you can see here, this is my Y component, this is my X component. If I take those and square root them, we're going to come up with that. And then guys, if we look for this degree measure, we take opposite over adjacent, which would give us tangent. So tangent theta equals 0.52342 divided by this. And if we take the inverse tangent of each side, we come up with a theta of 15 degrees. Okay? Which if we plug in right here is 15 degrees west of north. Okay? Do both techniques yield us with the same answer? Yes, indeed. And most kids, when I do this, they look at me and they're like, I want to do that one. Because that one is what? Easy. Okay? And guys, the next example we'll look at will sound something like this, just so you can see it in your head. If the puck is moving in the X direction at 15 meters per second, and then you put this force on it, how fast is the puck going to be going 3 seconds later? Well, if it's moving in one direction or in both directions, you can't just use this one. This is you can only use this when it's stationary. Okay, if it was moving, you'd have to do this method here. And your V naught would not be 0, it would be whatever velocity you have in that direction. And I'm going to show you one of those because I think it's one that you want to see, and it's really similar to your last homework problem. Okay? Any questions?